On pause. Okay, yeah. So just to put it out on records again, like we have agreed to meet at 6:30 p.m. Okay. And as we have been doing, the lectures will be a little longer than the normal duration of 75 minutes, just so that we don't fall in short of time later. Okay, so slowly we'll just keep on keeping the lectures a little longer rather than trying to keep more and more extra lectures. Fine. So my tablet is again not working. So I am going to share my script with you people and then we'll learn from there. Fine. I hope that would be better than trying to teach directly from the book. Okay.
Yes.
So let's start. Wait a second. Wow, great. So this also doesn't get detected. Oh, push. Okay, let's stop. What do you see right now?
Your screen with you scrolling to lecture 9 and
But you don't see the lecture 9 opened?
no, not really.
No.
Oh my goodness. What is wrong with this? Okay, let me just share this file with you people. So you open in your
Have you shared only the Explorer?
So from the Explorer, like I have opened in my desktop, I have a lecture 9.pdf open, but when I'm
Ma'am,
sharing,
are you sharing a window or are you sharing the entire screen?
I was
That's
sharing
your
a window, but in that window, this particular window does not pop up, which is very weird. It should detect all the windows. Let me try to do this again. Finally. Okay. So do you see lecture 9.pdf
Yes.
now? Is this visible?
Yes.
yes.
Okay. So just to continue from where we left off and what we have already covered, if you remember, we tried doing the number of ways in which the natural number can be written as a sum or like partitions of the natural number.
Yes.
Remember vaguely?
Yes.
So I will pick up from that same point and we will slide down in the topic of multisets today. Okay. So just to start with, the composition of n is a sequence a k-length sequence A1, A2, AK such that its entries sum up to n. So this way you're really writing n as A1 plus A2 plus so on up till AK, right? So that is one way of partitioning n, right? So this is a composition of n. What we are interested in is to find the number of ways you can do this. So we have already done this. Now we'll see another way to do this. So before that, if let's say I choose my 4, then this can be written as 1 plus 1 plus 1 plus 1. Is my mouse also visible?
Yes.
Yes, ma'am.
Okay. So this particular composition corresponds to this sequence, right? 1, 1, 1, 1. Ordering matters here. And then similarly, if I write 1 plus 1 plus 2, this corresponds to the sequence 1, 1, 2. And instead of 2 here, if I have taken it in between, because of course you will say, ma'am, does not matter if I write 1 plus 1 plus 2 or 1 plus 2 plus 1 or 2 plus 1 plus 1. But as compositions, they are making a difference because I am associating a sequence to them. And in a sequence, the ordering matters, right? It's a function into n. Okay, from n. So which location is being occupied by what number makes a difference. So this way there are how many? 1, 2, 3, 4, 5, 6. There are 8 ways in which I have written my n. So there are 8 compositions of n. 4. Yeah.
Yes.
This particular one is a 4 composition. These 3 are 3 compositions. These 3 are 2 compositions, and this is a 1 composition. Okay. Now, given some k composition alpha, which is alpha 1, alpha 2, alpha k of n, you can define a subset as take the one of the elements to be a1, which is, sorry, it should have been a1, a2, ak. It's not alpha 1, alpha 2, alpha k. So we'll make this change. So this is, oh goodness, a1, and these are ak. Okay. So when you take any particular k composition alpha of the elements a1, a2, ak, you associate a subset S alpha corresponding to this alpha given by a1, element a1 plus a2, element a1 plus a2 plus a3, and so on. The last element is a1 plus a2 and so on up till ak minus 1. Okay. So first of all, you see that this is a set where no 2 entries are same.
Yes.
Right? Also, what is this particular number? A1 plus A2 up to till AK minus 1. Can this be N?
No.
No. Why? Because one particular element AK is missing. And since all these AIs are natural numbers, so AK is at least 1. Right? So this particular summation is at max N minus 1. Correct?
Yes.
And how many elements are there in this particular set S alpha?
K minus 1.
K minus 1. Also, if you take a different alpha prime here and construct its S alpha prime, can you get the same S alpha? Given alpha not equal to alpha prime, can S alpha and S alpha prime be same?
No, like they will differ at least one place. Like at least 2 elements will be switched in the worst case.
So the sum will differ at one stage.
Okay, forget about the sum. My main thing would be at least one element here would be different, right? So let's say the first point you hit that different element is here at some alpha p, let's say. Okay, so till a1, a2, and so on, summation till ap minus 1, things will be same. But as soon as you hit the number when you have summation a1 plus a2 plus a3 and so on till ap, that number would be different for alpha and alpha prime, because ap and ap prime will be different.
Yes, yes, yes.
Is that right?
Yes, ma'am.
And then since you keep on adding more and more numbers, you can never get the same number back, because this particular sequence is an increasing sequence, right? A1 plus A2 is bigger than A1. A1 plus A2 plus A3 is bigger than A1 plus A2. So after up till AP minus 1, things are same, but after that, that increasing sequence itself is different. Okay, so the sets are different, S alpha and S alpha prime. Therefore, what we have actually achieved is a bijection which takes any alpha to S alpha. Okay, so this correspondence which I just showed here or told you here is a bijection. And if you want to see a reverse bijection, that if given some S alpha, there is a unique alpha which corresponds to it. I have to do, where is my cursor? Okay, so at least this we know that how many ways one can take these K compositions, K minus 1 choose and minus 1, because you are really just taking K minus 1 subsets of N minus 1, right? Using this particular bijection, I know that the number of K compositions of N is N minus 1 choose K minus 1. Is that right?
Yes, ma'am.
Also, if you want to find all the compositions of N, regardless of the number of ways, the number of boxes in which it partitions, as in here, this was a 4 composition. These were 3 compositions. So there are three compositions, 3 2 compositions, 1 composition, and 1 4 composition. But if you want to find all of these compositions of a particular number, you will have to sum over all the K compositions, where K would range from 1 up till N, right? So you do the summation of this starting from K going from 1 up till N, and you will get that this number is nothing but 2 raised to N minus 1, right? So a very quick proof that the number of compositions of any natural number N is 2 raised to N minus 1. But if you're particularly interested in K compositions, there are N minus 1 choose K minus 1 many such K compositions. Okay. Are you people with me so far?
Yes, ma'am.
Okay. So now for the reverse bijection, if you were working with the number N, take N dots. People who have had a course in discrete maths will like immediately relate this to bars and balls problems. But let's keep that hidden for now. So you take N balls or N dots, whatever, and then whenever you put these N balls in a line, there are how many in between spaces?
N minus 1.
N minus 1. So what you're actually saying is that to form any alpha, it really means I would put some bars somewhere, and those bars will make partitions, correct? If let's say I make a bar here and one bar here and one bar here, then how many partitions I have first of all?
4.
4. First is this partition, second is this partition, third is this, and fourth is this, right? How many elements are there in the first partition?
2.
2. How many in the second?
4.
In the third?
2.
In the fourth?
2.
So this corresponds to alpha equals 2, 4, 2, 2. Is that right?
Yes.
But if you recall, we said that we are trying to find a bijection from S alpha to alpha. Where is the S alpha? Well, I did not tell you, but it's already there. S alpha was the sequence where things were adding up, right? So this is my A1. So the first bar is being put after A1. Okay. The second bar is put after A1 plus A2, which is this. Third bar is put after A1 plus A2 plus A3, which is this. Last bar I don't have to put because I have already done enough job. Okay. So if S alpha was let's say 2, 6, 8, then what is this? You have clearly found that this is 2, then this is 4, then this is 2, and then this is 2. This is my alpha, right? So from this, I know I have to put a bar after 2 balls, which is this, after 6 balls, which is this, and after 8 balls, which is this. And after these bars have been put, you just take the number of balls you keep on hitting and write your alpha. Okay, so from S alpha, I have recovered alpha. And is this going to be unique? Given two different S alphas, so S alpha prime and S alpha, can I get the same K composition of the natural number that I'm working with?
No.
No, because there is a unique way in which you would put these bars, right? If the bar is here, it is here. It cannot have been the case that this is here or here, right?
Yes.
So this way, there is a bijection from S alpha to alpha also. So it's a two-way bijection. So this is another trick, like how last time we discussed, there are proofs which are called combinatorial proofs or the bijective proofs. Remember?
Yes.
This is a bijective proof in which we have given a bijection between two different entities of the system and then computed the number of such occurrences depending on the number of occurrences of this. Okay. So, okay, this is just a theory which I just explained. So you take k minus 1 bars and put in places that as corresponding to S alpha. So if n is 4 and S alpha is 1 and 3, you put 1 after this, and then for the next one, you don't need anything. Okay. Oh, I'm sorry. There is a mistake in this. Oh, I should have put one here because I have taken a K this thing. But you got the idea, right? So similarly for this, so this is pretty much like after A1 many points, you have put this after A2 many points because this whole as a whole is A1 plus A2. And up till here it is A1 plus A2 plus A3. So this way you keep on putting bars. Okay. Is that okay?
Yes, ma'am.
So as an application of this theory, so any doubts so far? Like, shall I pause and explain something again? This kind of a method will be used like many times and many problems you can solve with this. So even if you don't see me doing many of the problems here, there may be many which would appear in your quizzes or exams, assignments everywhere, not just for the course and even later. This gives a very powerful technique of counting balls and bars. If you're interested, you can even look up on Google problems with balls and bars, discrete mathematics. There are tons of ways to, utilize and even I would say manipulate this method. So you should read them. They're really interesting. Okay, as an application, if I give you this equation that x1 plus x2 plus and so on till xk, so k variables summing up to n, and I tell me the number of non-negative integer solutions to this particular equation. Then can someone tell me quickly?
Number of compositions.
Number of compositions, that's right. But just as a precautionary measure, if when we did the number of compositions, or rather, okay, since I said till xk, let's say k compositions, there we were taking only the those
Positive.
positive integers were there. Here, I said non-negative integer solutions, which means I would be okay if x1, x2 up till xk minus 1 are all zeros and xk itself is n. So that is also a solution. And that solution will be different from 0, 0, 0, n, comma 0. Right? Because remember I said that this ordering matters here. So just how 1, 1, 2 is different from 1, 2, 1, this 4 actually is not just a 4 here, but takes the form 0, 0, 0, 4. That is one way. Another solution is 0, 0, 4, 0. Another solution is 0, 4, 0, 0. Another solution is 4, 0, 0, 0. Right? So this itself corresponds to 4 different solutions if I was considering 4 compositions of the number 4. Understanding my point?
Yes, ma'am.
But we have done so much theory, so we are not going to let this go to a waste. So we are going to modify the equation. First of all, something like this, when you ask for the k compositions, but the elements can take values even from 0, such a composition is a weak composition. What we did was earlier called a composition. If they're allowed to take values as 0, it's called a weak composition. Okay, so what we are really being asked is the number of k weak compositions of the number n. Right? So suppose this number is called n of nk, just for the notational purpose. This is also from the book, the notation n, nk. So if you modify this particular equation and say that I'm going to replace each xi by xi plus 1, okay, and call that as a new variable yi. So I have modified this particular equation to y1 plus y2 and so on till yk, and then this will be equal to n plus k. Is that right? You
Yes,
have
ma'am.
added k many ones, correct?
Correct.
So you got n plus k here. Now, all these yi's, are they positive?
Yes, ma'am.
Yes, because they are being formed by adding 1 to something which could have taken the least value as 0. So yi's, all yi's are at least 1. Okay. So all yi's are positive integers. So these are natural numbers. So this particular equation now, the equation 2 is my k compositions of the number n plus k, right? Isn't that so?
Yes, ma'am.
And the number of solutions to this is going to be the number of solutions to this. Because this is uniquely determined. So this equation in between does not change a thing. So to find the number of solutions to this is equivalent to finding the number of solutions to this. But number of solutions to this is nothing but the number of k compositions of n plus k. Right? And what that number is? Quickly. Let me go back to the slide where we wrote this. So k compositions of n are n minus 1, choose k minus 1. Right?
Yes, ma'am.
Okay, so just in case you're finding it difficult, see, when I teach in this mode, like I have written my script already and I am explaining from that, I tend to go faster because my time of writing is saved. So I speak very fast. Okay, so if you're finding it hard, you have to slow me down. I will not realize that I'm going fast. Only when you do not answer promptly is when I would feel that, oh, maybe I'm going fast.
Okay, ma'am.
Okay, so don't feel like, oh, ma'am would think that we are not understanding or something. No, it's okay. Even if we cover less, it's fine, but you have to understand what we teach. So slow me down whenever you think that I'm like rushing or moving very fast. Yeah, I can't hear anyone.
Yes, ma'am.
Yes, ma'am.
So was I going fast?
No, it's fine till
No,
now.
ma'am, it's fine. Yeah.
Then why nobody was answering? Just sleepy after the lunch time? Oh, okay, not the lunchtime in your place right now. Okay. Yeah, so we were here. Okay. So this number of solutions to this particular equation is nothing but the k compositions of the number n plus k. And that is this number minus 1, choose this number minus 1. So it's going to be n plus k minus 1, choose k minus 1. Okay. And we had named it to be the n and k. So we found that n and k is n plus k minus 1, choose k minus 1. Okay.
Yes, ma'am.
Now, so if we modify further and ask how many equations, how many solutions are there to this particular equation? x1, x2, so on, their sum is less than equal to n. Instead of equals to n, how many non-negative integer solutions to this particular equation? So any ideas?
Like as we did above, we can vary n from 0 to n.
Yes,
And
the sum of all those capital N's.
Great, that is one way. So you find the solution for x1, x2 up till xk equals 0, equals 1, so on up till equals n, and then add them up. Well, one smarter way is to again modify the equation and say that I will put the number y here, a new variable y, which takes care of the deficit here.
Oh,
And then make this into a equality. So now the number of variables I have here is k plus 1. This is n. And now, since I'm still finding the non-negative integer solutions, for this particular new equation, I have to really find the number of k plus 1 weak compositions of n. Right? Recall weak composition was when the sum of these entries could be 0. Okay? So here when I have created this deficit, so first to be just as blind as you can go, this y itself could be 0. All right? Which is exactly
ma'am.
going to be the equation for this equality instead of inequality. So you are finding non-negative integer solutions to this. So this is same as the number of weak compositions of k plus 1 size for the number n, right? And that's what I do. So I take a b, again you have to remember this. So number of weak compositions turned out to be n plus k minus 1, choose k minus 1, right?
yes.
So now in this equation, k has been increased by 1. So here I will have a k plus 1 instead of k. And here instead of k minus 1, I will have a k. So I'm going to get n plus k plus 1 minus 1, choose k. So this is n plus k, choose k. That is the number of k plus 1 weak compositions of n, right? So in one shot, you have found the answer. Another way was what you suggested. You could go ahead and make this into n equations, or rather n plus 1 equations, equating this to be equals to 0, which gives you one particular solution, 0, 0, 0, 0, 0. And then going on, putting this equals 1, this equals 2, this equals 3, and so on up till n, you will get n different answers in this particular format, and then you would add them up. And ultimately what you get is this. Okay. So this way, actually, it's a nice observation in what you have suggested to me right now is that, so this is a combinatorial proof which you people have provided along with this answer, that if I did it through this is my answer, right? If I would have done it through the way that this summation equals 0, equals 1, and so on up till n, that would have given me something like this with a summation with n starting from 0 up till n, or let's say if I put a j here, summation j from 0 to n, right?
Yes.
So what we actually get is that summation, oh, I don't know, it's really hard to write. So, oops. Summation j from 0 to n, j plus k minus 1, choose k minus 1, this actually is going to be n plus k, choose k. Okay. You see what I did? I don't know if my
Yes, ma'am.
handwriting is even in the vicinity of being understandable. So this is what you have proved. So this was a combinatorial identity and we have proved it. How we proved it? We actually gave a combinatorial proof for this. And why am I saying this combinatorial? Because I came to this particular answer in two different ways. I showed that this is same as the answer for this particular equation, this particular question, and also this can be achieved from this as this. Okay, so in some sense, I should say that I counted this particular number in two different ways. And thus, this identity has been settled down. Okay, is this fine?
Yes, ma'am. Is this a common identity? Like I haven't seen this before.
Not a common identity, but it just clicked me that this is such a nice way that, see, more or less, this is how problems appear.
And holistic identity.
This may not be a very standard identity, but this is how combinatorial proofs go about. So when it came so naturally here through you and through the notes, I wanted to point it out that, see, this is how things work. So many times things will be just in front of us and we wouldn't notice, right? So if you knew something like this, and if you didn't know that something like this could happen, and you would have done this, right? And you would have arrived at this answer. And then if somebody told you, oh, see, look, you can do this directly, and within a shot you will get this answer. So this was nothing but coming at the number of solutions for this particular equation in two ways. So what is really being done? The number of solutions are being counted in two different manners. And this particular technique is really helpful when you do, let's say, extremal graph theory. I do not know how many of you would be interested or would take such a course in future, but if you do extremal graph theory, this is what happens almost all the time. Trust me, almost all the time. They will have bizarre looking equations and identities and whatnot, and when they prove it, it's so simple because they would just do a two-way counting. So something like this is called a two-way counting. You count something in two ways, and since you are counting the same thing, the answer you get from both the ways have to match up, right? Just how in childhood we used to do LHS equals RHS. Everyone would have done that.
Yes, ma'am.
Starting from LHS, now this is equals RHS, hence proved, hence QED. Everyone would have done this. So it's just like that. Something is there and you take it like you do from here. So there you are standing here. One way is to go like this, or another way is to go like this and coming back to it. Or you can be really very much enthusiastic and come like this. Right? But ultimately you're coming at this point. So if you want to see the distance is same. It's, or rather displacement is same. Only the path which you took was different. But the ultimate aim or the goal was same. Okay. So moving forward, this is what we achieved. Okay, and now we come to multisets. So if you, as in the last time also, I asked you the number of multisets or the concept of multisets, if you people are familiar with, and all of you were having a rough idea of what a multiset is. That much information is sufficient for us. So the main question is, when we talk about set or subset, we always say, okay, some element comes, and then once that element has come, we do not choose that element again, right? This is how n choose k works.
Yes.
You have some k boxes, you choose one element out of the n elements to fill the first box, and now that element disappears from the list of n elements. So to make the next choice, you are left with n minus 1 elements, right? Now that is the thing which I do not want to do. So what we really say is that, can I consider, can I keep on choosing elements even if I have chosen that same element earlier? So this really leads us to the question of considering k combinations of an n set with repetitions. Okay. So set S is having cardinality n, and T is a subset which you want to consider to be of cardinality k. And the question is, how can I really choose a k subset of T from the set S of n elements when I allow repetitions? And if at all, then how many such subsets will be possible? That is the question where we will end today. Rather, the answer to this is where we will end today. Okay. So far with me?
Ma'am, on the left side you've written K subset T. That means like it is not a set, right? That collection you take, it might have
So
repetition.
K subset here, when I have written, I said without repetitions.
Okay.
So this W/O in shorthand for me means without. Okay. If you see only a W with a slash, that means with.
Okay.
So as you have correctly pointed out, if I am allowing repetitions, I can't call it a subset. I will have to call it a multiset or a sub-multiset, depending on where I'm working. Okay.
Yes, ma'am.
So when I call this a subset, of course, I have not allowed any repetitions. Yeah.
Yes, ma'am.
So for such a choice, when I want to take k elements, possibly with some repetitions, I will say that this is nk. And remember, only a single bracket used to denote my choose. Now, since you have multi choosing, so you put multi brackets. Okay. So 2 opening brackets, 2 closing brackets. This would mean n multi choose k. All right. So if I take S to be the set 1, 2, 3, Can you tell me 3 multi-choose 2 for this? Write down quickly in your copies.
Nine.
No.
Won't we be having a 1 1 1 2 1 3 2 1 2 2 2 3 and 3 1 3 2 3 3?
3 multi-choose 2.
10.
Not 3 multi-choose 3. 3 multi-choose 2.
It's the answer 10.
Yeah, got?
Ma'am, it's the answer 10.
3 multi-choose 2?
Yeah.
No. So first of all, when I say 3 multi-choose 2, what is the cardinality of the multi-set you have to pick?
2.
2. And now there are 2 slots. These needs to be filled with the elements 1, 2, or 3 with possible repetitions, right? So to start you off with, I can tell you one such set, one such multi-set, and that is 1, 1. You please tell me another one.
2.
3
Okay. More?
3 3
Right. More?
1 2 1 3.
Right. There
I
is
think
just
that's
one
all.
more. Huh?
Oh, so 2 1 and 1 2 are same, right?
Yeah,
Yeah,
yeah.
then in that case we will have 6.
Correct.
Yeah.
See, we never said that the ordering matters. It's still considered as a set, which means ordering is irrelevant. Only thing is that now we allow repetitions. Okay?
Okay.
So you allow repetitions, but ordering is immaterial. So 3 multi-choose 2 has 6 elements. 1, 1, 2, 2, 3, 3, 1, 2, 1, 3, 2, 3. Okay?
Okay.
Now you have enough idea. Can you please compute 3 multi-choose 3?
This one is 10.
It would be helpful for you to, locate any missing pieces if you follow chronological order. Yeah, Saham, answer is right. Can you list out the elements?
1 1 1 1 1 2
Right,
1 1 3
right.
1 2 1 2 2
Mm-hmm.
3 2 2 2 2 2.
Hmm. Maybe right here. Let me start. 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 2, 1, 2, 3, 1, 3, 3. 2, 2, 2, 2, 2, 3, 2, 3, 3, 3, 3, 3, 3, 3. Did I miss something?
There are 10, right?
Yeah.
Yeah, so I did it like so with 3 elements, same we have 3 numbers with the with 3 elements distinct we have 1 number, like that we get 4 and with 2 same and the other one different, like that we can have 6 numbers, because we can choose the number which occurs twice in 3 ways and the number which occurs once in 2 ways. So 3
Okay.
plus 1 and plus 6 gets us 10.
Okay. So pretty much Riddhiman has done the same thing which he suggested us in the when we wanted to count the number of non-negative integer solutions to the inequality x1 plus x2 up till xk is less than equal to n. Okay. So while I was doing this, my immediate idea was to really see this as the number of elements in upper triangular matrices of that order. So when you were doing n multi-choose 2, it was really n cross n matrix, and the elements, number of elements in the half diagonal till the corner. So upper triangular, including the diagonal. And then if you're, let's say, having n multi-choose 3, you are actually in the matrix n cross n cross n, and you do the upper triangular including the main diagonal, and so on. Okay, everyone can have a different approach to it. That's fine. That's actually better. That way we get more answers, or more combinatorial proofs rather. Okay, so this we have verified already. Riddhiman has a proof, Saham has a proof, I have a proof. So I have done my homework. So Agilan, you are left.
Proof, ma'am, for what? Like,
So what we did was pretty much a proof, right?
yes, I thought like we can relate this to the composition series of 3 somehow. In this
Sorry?
case, like in the way you have written it down, you have stated from the smallest number, right? Counting that way was making it easy. I wrote it randomly, but I lost.
So this I did. So you see a tiered out page from here. This is
Ah,
because I messed up a number of times.
oh, I see.
So this is the neatest way I could come out with. And that's why I told you in the beginning that if you write them down in the chronological order, it's hard to miss. And then as soon as I wrote it in this fashion, it clicked me that this is nothing but the upper triangular entries of a matrix. So that's what I just shared with you people, that if this number happens to be 2, it's nothing but the upper triangular matrix along with, so this is the diagonal, right? This is diagonal 1 up and this is topmost. If you try to see it that way. It's not
Yeah.
written in the most neat way possible, but this is how it occurs, right?
Yes, ma'am. But when k is greater than 2,
Then you are having higher dimensional matrices.
yes, ma'am.
So n cross n cross n, and there you will have to see the main diagonal and then all the diagonals above it.
Yes.
Or below it, whichever one, but one of them you have to, the one of the directions you choose and go on in that direction. Okay, so this particular one I computed using this trick, that I would take the diagonals and then count it, and answer came out to be 10, and then I verified for myself through a brute force method By brute force, it means I listed out all the elements of this particular multiset and verified that this answer is indeed 10. Okay, so that's how I have a proof of this. Riddhiman gave his set of proof that he will do it part by part, that number of elements in this particular multiset which has number of threes as 1 or number of threes as 2, and then he'll may put a counter on the occurrence of other numbers, right, Riddhiman?
Yes.
But there might be repetitions, right? Like if you take n multi-choose n by 2 or something, then
Yeah.
clearly,
So he's doing that.
okay.
He's
Yes.
recursively doing it.
I mean, in his counting, there might be some repetitions, right?
No, if you
Okay.
fix that the number of threes that occur in my number is just 1, let's say, then these are the two elements you would hit. So after the 3 has been removed from this, the remaining set, or rather the remaining elements in this set, they are going to be different, right? Otherwise, these two sets would be same.
Yes. Ma'am.
So once you are dealing with, so this worked for, I mean, he could do this very fast because we already computed 3 multi-choose 2. So to compute 3 multi-choose 3 through the Riddhiman's method, he would need to use 3 multi-choose 2. Right, Riddhiman?
Yeah, I actually kind of I didn't think of it that way. What I did was I checked the number of numbers where first I checked the number of numbers where all the 3 digits are different, and that can happen only in one way, 1, 2, 3. And then
Right.
I checked the numbers where all the 3 digits are same. That can happen in 3 ways: 1, 1, 1, 2, 2, 2, and 3, 3, 3. So like that, I got 4 numbers. And then what I did was I would have to consider the cases where there are two digits coming up. Like one digit occurs twice, and the other digit occurs once. And that can happen in 6 ways, because I can choose the digit which occurs twice in 3 ways, and then I can choose the other digit in 2 ways. So
Yeah, but there is a small problem here, right? Like if you take n to be 4 and k to be 2,
Yeah, I was about to say. So
yeah,
he
that
got
was
lucky
what.
because they were dealing with just 3 numbers.
yeah, that's true.
So if you had a higher n, then this method wouldn't work. You will have to really come down to the point that what we were just discussing, that to
Yeah.
find n multi-choose k, you would be using n multi-choose k minus 1. Which is even better because by now you know how to, really break down your problem at hand to something for which a smaller value works. Right? This is how initially we computed the number of k compositions of n anyway. Isn't that so?
Yes.
Or even in your assignments, when I asked you to find the number of subsets which do not have two consecutive elements.
Yes, ma'am.
Just for the extra information, such subsets are called alternating sets or stabilizing sets. And if at all you people are ever interested in Kineser graphs and their theory and their chromatic number, maybe in some extra, off this course, we can talk about it. Stable Kineser graphs are precisely the subgraph of Kineser graph which are formed on the vertex set where the elements are such that no two consecutive numbers are present in the vertex set. And these stable Kineser graphs have a really, really rich theory in the sense of chromatic number, in the sense of vertex what is this called? Vertex cut and lot more. It seems like the stable Kinesis graphs have enough information that one does not have to even look at the full Kinesis graph. Its subgraphs, the stable Kinesis graph of it works well enough. But okay, that's too much of a deviation from the main topic. So coming back to this, if at all you're interested, I can give you pointers to YouTube videos. I think this might be there in 1 or 2 lectures of mine also from previous course. But nevertheless, okay, coming back to this. So we know that 3 multi choose 3 is 10. All of us have a nice proof, and now see something which will blow our mind. So before that, some particular notation. So multiset is nothing but a set with repeated elements. So this is the symbol for with. I was telling no. W with a slash is with, W with a slash and O means without.
Yes, ma'am. Yeah.
Okay, so finite multiset M on a particular set S is actually a pair S new, where new is a function from the set S to the set of whole numbers. N0 is the set of whole numbers, which means natural numbers union 0. Okay, so what this really defines is the number of repetitions a particular element is getting repeated for this particular set, multiset M. Okay, and since I said finite, what this should be, that when I run over all of my S, the values of new S should sum up to be finite. Okay. So if let's say S was 1, 2, 3, as in this example, so for this particular M, the function S new is, S is this, new is the function taking 1 to 2, 2 to 0, and 3 to 0. Okay.
Yes, ma'am.
Understood? Similarly, if I have to consider this, for this, new will take 1 to 0, 2 will go to 1, and 3 will go to 1, right? And you see this number, with what you get here, all these numbers, when you add up, gives you the cardinality of this particular set. Is that right?
Yes.
So given the set S, what new you choose defines a finite multiset. Okay?
Ma'am, if S is itself finite, then
Sorry?
if S is finite, then we don't want the condition that the summation should be finite. I mean, new can take finite values only, right?
Yeah, but we are not putting any restriction on the set S. For instance, this S could be N itself.
Yes. Okay.
In such a case, I will have to restrict to make this into a, sorry, this is bothering. Okay. So to keep this in condition intact is necessary for me to make sense of a finite multiset. Because this is some set. I don't know what set I'm going to work with. What really matters to me is that ultimately this is what happens.
Okay.
Okay. And even otherwise, like even if you take S to be finite, it's really, for the calculation purposes, it's better to keep this in mind so that you don't have to really worry about, oh, since I'm going from a finite set and it can take any finite many values only, so this is going to be finite. So all those we already know, but just for the safety purposes. Okay. So this I've already told that when you sum over all the new x running over the set S, this gives you the mod M, which you know means the cardinality of M, or hashtag M. This is not the hashtag which you see on Facebook or Instagram. This is the mathematical hash, which means number. Okay, hash means number. Hashing function you might have seen, computer science guys. Or card M means cardinality of M. Okay, so this M then is the multiset x1 raised to new x1 times, which means x1 is repeated new x1 times. This new x1 may as well be 0, which means x1 is not present in the set. Okay. Similarly for x2 and so on till xn. x1, x2, xn were the elements of S. So S was x1, x2, xn. Then M given new is x1 raised to new x1, x2 raised to new x2, and so on till xn raised to new xn. Okay. So if the cardinality of M is k, then you call M to be a k multiset on S. All right. Now, if you have two multisets, one is M, another one is M prime, can there be some relation between M and N prime? Can you say that M prime is a multi-subset of, or rather sub-multiset of M? Yes, we can. Condition is that remember, some multiset means it's a pair S nu. Okay, so now when you are dealing with two multisets M prime and M prime comes with some function nu prime, M comes with some function mu. So if mu prime of x, which is this, happens to be less than equal to mu of x for every x, then you say that M prime is a sub-multiset of M. All right?
Yes, ma'am.
And very quickly we can see that the number of sub-multisets of a set M is this number. Because for every element x, you have nu x plus 1 many choices. Nu x is a starting from 0 to k. It gives you at max k many values here, and since 0 does not really gets counted, for that I have to add a 1 here. So nu x plus 1 many choices for each of x, and then you multiply this entire number. Right?
Yes, ma'am.
So this is the number of sub-multisets of a particular multiset M on the set S. Now, K combination of S with repetition is a multiset on S with K elements. Is this fine? So the K combination which we started off with of a set S. So K combination earlier we actually started of a number, right? Right.
What do you mean by a K combination? The C.
So this particular combination. Oops, sorry.
Okay.
I should, so something like this.
Okay.
So these are elements coming with some sort of, multiplicity, right?
Yes, ma'am.
So where am I? So if you take a K combination of S, which means you take a subset of S, okay, with repetition, this is actually nothing but a multiset on S with K elements. So elements of S you have taken and you form combinations out of them, allowing the repetition. This is giving you nothing but a multiset on S with K elements, right?
Yes, ma'am.
So this was a 2 combination of elements of S. This was another two combination of elements of S. This you agree, right? These are like what you say as words or strings. So those are combinations, right? Therefore, the number of K multisets on a set S is going to be this particular number. This you people agree or not? Take your time. Understood? Since I don't hear any voices, I should assume that it's not clear.
This is how we define n multi-set.
No, this is not how we defined a multiset. We defined a multiset as a pair S comma nu, where nu was a function taking values in n0. This is how a multiset was defined.
Yes, ma'am, but the term on the right side, n multi-choose k.
Yeah.
This
was the notation which said that in how many ways can you choose k elements from n allowing allowing repetition. This was a notation.
Okay.
So far we have not done any mathematics with it, right? We don't really know what this number is, otherwise writing this would have been easy, no? We would not have to had to really list this out. No, we would have directly written this number, isn't it?
Yes.
So n multi-choose k is certainly, I agree, is the number of k multisets on a set with cardinality n. Now, what I'm asking is different. This is that this number is actually equals to this. So if you can if you are convinced that this is equals this, then this being equals this should come easily, at least in your head. And if not, we have a proof. This I would suggest go back and try to relate this with the number of non-negative integer solutions problem that we started off with. Okay. And from there, independently, you should be able to prove this. And I am here giving you another combinatorial proof, and then later we'll see one more application of this and end this lecture. Okay. So
Okay.
if you have chosen A1, A2, AK in strictly increasing order to be some k elements between 1 and n plus k minus 1, then this A1, A2, AK gives a k subset of n plus k minus 1.
Yes.
Okay. Now put bi to be ai plus 1 minus I. So my first condition, or rather my first observation is that each of these BIs is at most n, even though my AK could have been as large as n plus k minus k, n minus 1. BIs are at max n. Why so? Because from AI you are reducing I. So from AK, at least K is getting reduced, right? Is that right? Since these are strictly increasing order, so A1 is at least 1, right? So
Yeah.
A2 has to be at least 1 bigger than A1. So A2 has to be at least 2, correct?
Yes.
So AK is at least K.
Yes.
And that is the smallest possible number available for AK, right? So when I'm subtracting here, I have to see what happens if I would have done this on the, if I would have subtracted smallest possible number, that is when I am going to hit the largest possible number for my BI, correct?
Yes.
So this is where I would have had hit the highest possible AK and the lowest possible value for, so this is the K which you would subtract. So from AK, K goes. So even if AK happened to be N plus K minus 1, the largest possible, you subtract K from it, you're left with N minus 1, and then you add a 1 here. So BK is at max N. Convinced?
Yes.
Is that clear? So each BI is less than equal to N. However, depending on these AIs and these Is, you may have that some BI is same as some BJ. So this is actually giving you a multiset. How many elements are there? K many elements are there. So it's actually a K multiset on N. Okay. So any element, when you start from here, it's giving you an element here. Correct? So if you chose a K element subset of N plus K minus 1, it gave you a K multiset of N. This way. Now the other way around, if I have to show that something here gives me here, if you start with a K multiset, B1, B2, so 1 less than equal to B1 less than equal to B2 and so on, less than equal to BK less than equal to N on this set N, and just the reverse of this, put AI to be BI plus I minus 1. So BI maximum would have been my BK. You're adding a K and a minus 1. So N plus K minus 1 is the highest it could have hit. Therefore, A1 plus A1, A2, AK is a K subset of N plus K minus 1. Now, this number actually is unique for every I. Because even if two BI and BJs were same, the additional factor which you have this here, I minus 1 and the other one would be J minus 1, that would make AI and AJ different. Okay. So this is actually a subset and not a multiset. So, but how many elements? K. So K subset of a N plus K minus 1. Therefore, you started with a K multiset on N and got a K subset of N plus K minus 1. Thus, these two elements are same. These two numbers are same. Okay. Okay, I seem to be running out of time. So just go through this once again on your own and you'll understand this. It's not at all hard. But what we did here is that, so definitely this was a bijective proof. Again, I showed a bijection between the K multisets on number of K multisets on N with the K subsets of N plus K minus 1. Okay, so this was a bijective proof, a combinatorial one. And the technique, what we really did was we started with a strictly increasing sequence of AIs and reduced it to a sequence of BIs which were less than equal to. So from a strictly increasing sequence, you got a weakly increasing sequence. BIs were weakly increasing, right? Some BJs could be same. So such a technique is called compression. This kind of a thing we used earlier also when we had done this addition here. From something which could have hit a 0 here, now you have come down to something which does not hit a 0 and are always in the positive side. So such a technique is called compression, where you convert a strictly increasing sequence to a weakly increasing sequence. Now, to see a generating functions approach to it, if S is the subset x1, x2, xn, then the product of these series 1 plus x1 plus x1 square and so on with the series 1 plus x2 plus x2 square and so on, all the way till 1 plus xn square and so on. This is nothing but the summation of this entire quantity, and this summation runs over all the possible multisets of S. This thing is clear. This is just the way of writing. So x2 square is nothing but x2 raised to this particular number for this particular m. So when you expand this out, only one of the terms will be 1 and rest others will be monomials in x1, x2, xn, right? And each of these monomials can be expressed in this fashion for some or the other nu. So
Yes.
in a compressed manner, I have written this full huge product as this. Okay. And this is always finite. So this inside thing I have kept as summation xi in S nu of xi to be finite, so that each m is finite. Now, so this here it was needed for me, right? Otherwise, this could have been like how this would go, and then you would not know the degree. So as a whole, the degree should always be finite. Now, putting xi's to be x in all of these brackets, what you get really is 1 plus x square plus x cube and so on into the same thing, into the same thing, into the same thing. How many times? N times. So you have this bracket raised to n, which is same as now xi being replaced by x, you get x raised to nu of x multiplied how many times? Whichever number of times it comes from here. So how many elements are there in M is the power here, right?
Yes, ma'am.
But this I know how many multisets are there? N multi-choose K, x raised to K. So K running from 0, N multi-choose K, x raised to K is this number. Now dissecting this further, I know this inside of bracket is 1 minus x raised to minus 1. So then along with this power n, I have 1 minus x raised to minus n. Now using the binomial expansion, this is actually summation k from starting from 0 minus n choose k minus 1 raised to k and x raised to k. Okay. Now, if I compare the component wise here for the powers of x, what it tells me is that n multi-choose k, which is this, is nothing but minus 1 choose minus 1 raised to k times minus n choose k. But I knew that n multi-choose k was n plus k minus 1 choose k from this slide here. Right? So n multi choose k independently itself is n plus k minus 1 choose k. Therefore, this number being equal to this, and from here we computed it to be equals to this as well. So this is actually a reciprocal combinatorial identity. So you are really seeing what happens when you shift from n to minus n and subset to a multiset. So more of such things will be covered later, possibly or not. I'm not very sure if the time allows. It comes really late in the course. Course as in, I mean, it's not part of the course, but I wanted to show this identity so that if you are more interested, you can see more of it. This is in the 4th chapter of the enumerative combinatorics. Well, yeah, this is the main thing. Like you started with something which you know, and then you keep on evaluating both the sides and come down to something of this form. When you compare the components, coefficients of x raised to k. Remember in the ekdams, in the very beginning, we said that two series are equal if the powers of x matches. The coefficients of the x raised to k are same for every k. So if they are equal, better this be equals this. So you get this. Okay. And another way to see this is that this number is also equals to this number. Weirdly enough. Okay, so this is where I end today. And maybe I'm not very sure, but if at all it happens that I have to upload a lecture without really engaging you people in between, I will upload a recording of it and release the notes and notify you people. Okay.
Okay.
This
ma'am.
is extra from the usual Wednesday and Friday's lectures.
Okay. ma'am.
I
Okay.
mean, if you do that, you can inform us the time you are doing, and we can, if possible, if we are available, we can come at that time, I guess.
Yeah, that could be done, Ridhiman. Only issue is that I'm not very sure what time I would do. And
Okay.
then, I mean, I find it a little inhuman to, inform you guys just 20 or 10 minutes a priori to me starting the lecture. That's why I said so.
Okay.
Yeah,
But
as
still,
of
I think you can, if possible, check if any of us is available. I think that will be better. If,
yeah, I shall surely give you a call, Ridhiman.
okay. Okay.
Okay, so like I plan not to do so, but if at all like for my next lecture, if I see that the material is getting too much, I may do this. Okay. And this lecture's recording, the video recording, you may not see very soon. Maybe this will come out only on a Monday, on the coming Monday.
Okay.
Okay. But yeah, lecture notes I will share right now. Okay.
You have already shared it in WhatsApp.
As in, I will put it in Moodle just
Okay.
for the records. WhatsApp is not so formal, no?
Okay. Yeah.
Okay, ठीक है. And so, yeah, assignment possibly tonight or tomorrow you will get. Assignments I have already returned back. Next assignment I was talking about right now. So assignment 2 will be released by tonight or tomorrow night. Okay.
Okay.
And as I told before, quiz will be somewhere in mid of November.
Okay.
Okay. ma'am.
Okay. Expect quick questions in the quiz.
Okay. ma'am.
All right. Okay, chalo. Bye-bye.
Bye. Ma'am.